All right, you're back for the second video of the day, and again, I'm sorry we have extra videos, but hopefully we'll make up for it by having a little bit extra time in class to work on problems and things like that. Um, but okay, in this video, we're really going through 1.3 in the textbook, and again, just like before, you should read 1.3. And you should look through it. And a couple of these theorems are really big and the proofs are kind of complicated, but I actually want you to take the time to read them and try to understand them. It's a real sign of mathematical maturity when you can read and understand these proofs. Okay, this part, we're going to have problems. We're going to have two definitions which are probably new to most of you. The idea of an infimum and a supremum. And we'll really focus most of our ideas on a supremum. These things are like a neighbor to a max and a min, right? So they're kind of connected ideas, but they're not the same idea, and we'll see how they're not actually the same. But let's start with this idea of a supremum and kind of define what it is and think about it a little bit. Okay, so the supremum, if I have a set, and let's start with the set E, 1 over 1 minus n, and let me just like draw this set on a graph. Well, notice if I put 0 here and 1 here, I can just start plugging in values for 1 minus 1 over n. So if I put n equals 1, I get 1 minus 1, which is 0, so I get a dot right here at 0. Now, if I put 2 in, I get 1 minus a half, which is a half, and so that gives me that dot. If I put 3 in, I get 2/3, 3/4, 4/5, and you can kind of, at this point, start to see what's happening. What's happening is we're getting more and more dots, and as we're getting them, they're getting close to this number 1. So if I were to ask you, just really quickly, what are all of the upper bounds to this set, to these set of blue numbers? So what if we want all upper bounds? What are all upper bounds of this set? Well, okay, you would go, well, it looks like all upper bounds are the number 1 and anything bigger than 1. So everything 1 and up. We might write this as the set that looks like this, 1 to infinity. Notice 1 is an upper bound because every one of these values are always smaller than 1. But you can also kind of tell, if you realize, if you think about it a little bit, that if you pick any number less than 1, that's not going to be good enough. So you pick like 0.999, well, eventually these values get bigger than 0.999, so 0.999 is not an upper bound. Okay, so once we have all upper bounds, we're ready to start figuring out what the sup is. The sup is the smallest of the upper bounds. We often use the phrase in mathematics, we often say the sup E is the least upper bound. So of all the upper bounds that you have, the sup of E is the smallest of them. Okay, now this isn't always true. You don't always have an upper bound. So if you don't have any upper bounds, then you obviously don't have a sup, and it's not part. And sup is just short for supremum. Similarly, the infimum is the opposite. So the infimum is, we take all the lower bounds. The infimum is the largest of those. Okay, so if I want to do this, I want to write a definition. Let's try to make my definition kind of a nice one. And the way I'm going to write it is this. I'm going to sup A equals S satisfies two properties. And this is a little bit different than what the book wrote, but it is the same. It's just in my own language. So the sup E satisfies two properties. Number 1, it has to be an upper bound. And what do I mean by that? Well, that means for all elements in E, and let's just use, let's use an X. For every X in the set E, S has to be greater than or equal to that X value. So in other words, you pick any number in our set, any of these blue dots, and our upper bound, which we're thinking is probably going to be the number 1, is bigger than every single blue dot. Now the second property is that it's the smallest of all the upper bounds. And how do you say it's the smallest of the upper bounds? Well, the way I'm going to do it is I'm going to write it like this. I'm going to say that if m is a real number such that for all x in E, m is greater than or equal to x. So in other words, if m is also an upper bound, then s is smaller than m. So what did I say with these two phrases? The first phrase I said is s is an upper bound, and second I said if you have any other upper bound like m, that upper bound has to be bigger than s. So if it satisfies these two properties, that makes it a sup. And so we can see from this we can see from this example right here that that the sup of E here needs to be the number 1. All right, and then once we have a sup lined up, we're ready to have some theorems, and we have two theorems that the book points out that are really simple to prove. So what if we don't even worry too much about proving them? I'll just kind of walk you or tell you verbally about the proof. So the first theorem is this. The first theorem says if the sup of some set equals S1 and the sup is also equal to S2, then S1 equals S2. This is theorem this is theorem 1.13, and the book words it in a more kind of casual phrase. So the book says, if a set has a supremum, then it has only one supremum. So what does that really mean? It means that, well, if it has two supremums, then those two supremums have to be equal. Real quick note, this is kind of how mathematicians interpret this language. So if anyone makes a claim that some function or some set has only one, then what we usually do is we usually assume that it has two and prove that those two must be equal. Well, how would I know that these two sups have to be equal? Well, really, the heart is that both of them, both S1 and S2, satisfy property 1, right? They both satisfy property 1. And so property 2 says that S1 has to be less than or equal to S2 because S1 is a sup, but also because S2 is a sup, S2 has to be less than or equal to S1. And the only way that S1 can be less than or equal to S2, and at the same time S2 is less than or equal to S1, the only way for this to happen is if the two are equal to each other. So that's really at the heart of this theorem, and I would encourage you to kind of look at the book and see if that makes sense, how they write it up. But that's really what they're getting at. Okay, so let's kind of look at our second theorem, which I thought was interesting. And this theorem is 1.14, and it's called the approximation property for suprema. And so the approximation property looks something like this. And it says if epsilon is, or for all epsilon greater than 0, for all epsilon greater than 0, there exists some element A in our set E. In our set E, such that the sup of E minus epsilon is less than A is less than or equal to the sup of E. Now, let me think about what that means, and let me start by drawing a picture. And the way this picture is going to look is if I had a graph like I had earlier, where I have a bunch of points, say, getting very close to one point, just like I had a moment ago, and we have a sup over here on this side. And suppose this line is the sup, so that'll be my S. Then what happens if I move that line, say, just ever so slightly to the left? So what if I move that line leftward just a little bit, just to become S minus epsilon? Well, notice that if this thing is really a sup, then that means that we have some points located between that line that got moved backwards and our line that is our soup. So that means this theorem just clearly has to be true. But that means that if you move the line backwards, you can always find a point that fits in between these 2 points. This ends up being kind of nice and useful sometimes. But there's a few automatic consequences of this. The first one is that if your set is made up of integers, then that means the soup itself has to be an integer. And we can see why this is the case, because if you took your soup and just moved back like half a unit, then you would have had to have lost a point. Otherwise, you wouldn't it wouldn't be the soup anymore. So you can kind of see how integers have to have integers themselves as the soup. Okay, I feel like I'm babbling a little bit. But at any rate, let's move on and talk about the completeness axiom. And this is kind of the last axiom that we'll talk about for the real numbers. And the completeness axiom basically says this. It talks about sets of real numbers. And it basically says this. If E is a set of real numbers, so E is a subset of the real numbers. And two things are true. If E is not non-empty, so usually we always have to write this at the beginning of a statement because there's not a lot interesting about the empty set. So we always want to assume that our set is not empty. But if it's not empty and we want another thing, and we want it to be bounded above. So if it's not empty and it's bounded above, then the soup of E, which I'm going to call the letter S, exists as a real number. That's a bad looking R. So exists as a real number. Then the soup E, which equals to S, is a real number, is a finite real number. Okay, so what that means, if it has one bound, then it's gonna have a lot of them. But once it's not empty and bounded above, then you know it's got to have a soup. And this seems pretty logical, right? So it seems like if I took a bunch of points like we had before, and those points have an upper bound somewhere, then that means that somewhere over here there's going to be your smallest upper bound that those points are getting close to. Or it could actually be one of the points themselves. I keep drawing it like we have some sort of limit here, but we don't necessarily have to have that. It doesn't have to be exactly that point. So this is the completeness axiom, and it's a really nice result. And what's nice about it is it lets us to go about proving certain things about sets. So I'm going to walk through two proofs that are rather complicated, but really both of the proofs hinge off of one central idea. And it just hinges off this central idea right here. What do we do first? So first we define an interesting set. We define a set. And what's always makes these problems interesting and hard for students is that it's not always clear how that you define the set or where this set comes from. But again, this is a fairly common thing that happens throughout mathematics. So the first thing we're going to do is we're going to define a set, and then we're going to show that it is not the empty set and that it is bounded above. So if it's not empty and bounded above, then what does that mean? That means it must have a soup. But now once we know it has a soup, or once it has a supremum, then that supremum, we can use the properties of the soup to solve our theorem. Of the soup E for our theorem. So this is kind of a general way of proving theorems. Now, let me say these are fairly complex. So these are theorems that usually we don't ask students to do independently. However, as you grow in your mathematical ability, you'll get to where you can tackle problems like this yourself. And maybe that's this semester. Maybe you're already good at this. If not, I hope you kind of keep going to the point where you can tackle things like this. So let's start with the first one of these, and I'm not going to work out all the details of this theorem. This is theorem 1.17 in the textbook, and so what you should do is you should find theorem 1.17 and kind of look at it and read along and look at the details of it, and then compare the details to what I'm going to sketch out for you. So I'm just going to sketch out a picture of what this theorem is. And this is called the Archimedean principle, named after Archimedes, who is really one of the greatest mathematicians of all time, an ancient Greek mathematician. Learn about him if you're interested. He's really pretty fantastic. Okay. But it says this: if we have real numbers with a being greater than 0, then there must exist an integer such that b is less than n times a. Okay, so what's going on with this? Why is this an interesting theorem at all? Well, what this theorem says is that if we have the real numbers here, which can be they can be very big. So the real numbers have some really small numbers. They have some small numbers that are really, really close to 0, 1 billionth. And they have some really big numbers that are unfathomably large. So if you're interested, go read about a number called Graham's number. And what you'll find is that this is a number that if you were to take every atom in the known universe and write a digit on it, you wouldn't be able to write down the Graham's number. Actually, you wouldn't even be able to write down how many digits are in Graham's number. It's just so unfathomably large how big that number is. So there are numbers out there that just dwarf all of our imagination. But the point is that if I take any number, and let's make our a number really, really small. So if I take any number a that's really small here and take some number over here, b, that's really, really big, and then I start multiplying a by integers, eventually a will get big enough to where you're finally past b. So eventually at some point down the road, a passes b. This might seem kind of obvious to us, but notice this actually tells us something about the nature of numbers itself if we assume this is true. And this means that there doesn't exist any number that's like infinitesimally small. So one thing that early mathematicians thought about a lot was what we might call the infinitesimal, and you might call it either an epsilon or a dx or something. And that is, so that means that if you had a number like epsilon, which is 0.00, and then we have an infinite number of zeros here, 1. Infinite number of zeros. So the question is there a number that looks like this, that we have an infinite number of zeros and 1? Well, if the Archimedean principle is true, then such a number couldn't exist, because it doesn't matter how big you can multiply it by any number you want, and it would never reach like 1 or 10 or 100 or something like that. So numbers like this can't be actual real numbers if the Archimedean principle is true. Well, let's kind of dig a little bit further into the Archimedean principle and say what are we actually going for here? And what we're actually going for is, what we're going to do is we're going to kind of break this thing up into a bunch of chunks and think of, well, we got this region here, and then we're going to just keep breaking it up and just keep adding those a's to each other. And we're just going to keep adding all of them together until we get to b. And then we'll stop right when we get to b. And so we'll have a last element that is smaller than b. And so we're going to let E be our set of all n. Actually, I think the book uses k, so let's stick with the same letter that the book uses. All integers k, such that, and again, such that k times a is less than or equal to b. And what that means is that E is this set. E is kind of this set of green stripes that I showed here. And what we're going to notice is we're going to notice that, well, that set has to have two properties. First, that set must be non-empty. Empty doesn't have a B in it. What am I thinking? Okay. That set must be non-empty. Okay. Why does it have to be non-empty? Well, you actually break the problem up into two pieces, and you go, well, if A is bigger than B, then this theorem is true trivially, so we don't have to worry about the problem. But if B is bigger than A, then n equals 1 has to be in our set E. So n equals 1 has to be there. So this thing is non-empty. And then the second thing that we're going to notice is that this thing definitely has to be bounded above. So since it's non-empty, and since it's bounded above, by the way, it has to be bounded above by B, because we've said that we're only going to use the elements that go up to, well, not by B, but okay, it's got to be bounded above, and look a little bit closer at the theorem, and it'll kind of go into the argument for that. But once we know that it's non-empty, and we know that it's bounded above, then that means that the soup must exist. And if you can see my picture, this right here is that soup. So now what are we going to do? Well, we're just going to add 1 to that number. Okay. So by the way, the S isn't the soup S isn't the number. The S is the K value. So this would be S times A, and so S would be the soup. So this S times A is that value. Okay. So we hit that soup, and then what we're going to do is we're going to move just to the other side and say, well, what happens if we move just on the other side of that soup? So what happens if we add one more section? Well, if we add one more section, we get plus 1 times A, and now we have to be bigger than B. And so now all that's left in the proof is kind of going through the details to prove that once we added that 1, we absolutely got a point that's bigger than B. So again, look at this theorem and read through the theorem and kind of see for yourself how the book takes this picture and turns it into kind of a nice little proof framework, or not proof framework, but into a nice proof. Okay, I want to add 2 corollaries about the Archimedean principle. Oh, I didn't want to delete all that. Okay, so let's leave it. So I want to add 2 corollaries about the Archimedean principle, and you all probably know a corollary is just a result that follows immediately from it, but these are both really worth kind of noticing. So corollary number 1 says, well, what if we just let A equal 1 in this theorem that we have? Well, if you just let A equal 1, so that's this part right here, then that means that for all B in the real numbers, there exists a natural number n such that B is less than n. So that means there is no real number that's bigger than every integer. You can always find an integer bigger than a real number. This is intuitive, right? This is something that we kind of think should be true automatically, but it's something that mathematicians, we like to have a proof. We like to have a way to be confident of this. So, for example, this tells us that infinity isn't a number. Infinity is a process or an idea, but it's not a number. Numbers there's always integers that are larger than them. Okay, the second corollary comes from what would happen if we wanted B to equal 1. And notice if we do B equals 1, then it says for all A greater than 0, there exists an n such that 1 is less than n times A. But let's rewrite that one time, and let's just rewrite that. That means that 1 over n is less than A. And so what is this telling us? This is telling us that if I have 0 here and I have any point A, I can always find some integer 1 over n inside of it. So it doesn't matter how small my point is, I can always make a fraction, an integer, a 1 over n integer smaller than that. Ah, there goes my cat again. It's because I haven't fed her tonight. She's really upset. Okay, and she's very old. Our cat is 19 years old. Okay, so this is the idea of the Archimedean principle, but this last point is being able to always sneak a 1 over n integer inside of any real number is actually tells us something about the relationship between fractions and real numbers. And this is what we get to when we get to maybe the last big idea that we're going to talk about today, and that is the density of the rational numbers. And this proof is also in the book. This is 1.18, and I would suggest again that you go look at that and kind of read along. When you look at these proofs, they're going to feel a little convoluted. There's going to be a lot of letters, a lot of craziness going on, but keep the big picture in mind. And when you keep the big picture in mind, then you'll be able to see through the proof and kind of see all the details that are going into it. But what does density mean in real numbers? Well, density means this. It says for all real numbers, a and b, there exists a rational number, q, such that q is between a and b. That should have been a q is between a and b. Oh, I should have added, sorry, instead of saying for all a and b in R, I should say for all a less than b, right? So if a is equal to b, then that throws the whole thing off. But as long as they're not equal, as long as one of them is less than the other, then there exists a q that's between it. So that means if I draw my number line and I put any two numbers, so I put a, I can put b as close to a as I want. It doesn't matter how close they are on my number line. I can then come and find a rational number. So that means I have a fraction, something like m over n. I can find some fraction that sneaks in between those. It doesn't matter how small that fraction is. I can always pull this off. Okay, so here's the question: how are we going to make this happen? And the answer is using a real similar method to what we did last time. And that is, I'm going to start with my number line. And let's put 0 here. And then let's put A over here and B over here. And then what I want to do is I want to pick some small n value. But I want to pick an n value that makes it where 1 over n is smaller than this gap. So I want 1 over n to be smaller than this gap. 1 over n fits in here. Okay, and so then the big idea now is if 1 over n is smaller than this gap, then I can put 1 over n here, 2 over n here, 3 over n, 4 over n, and I can keep going, and then eventually I get a 1 over n that fits within my region itself. So this is the big idea of my proof, that I'm going to make that really small, make appropriate 1 over n number that's small enough, and then go along until I get it to work out the way that I intend. Okay, so how do I choose my 1 over n? Well, the answer is I have to look at two numbers, and I choose n so that it's greater than the maximum of 1 over a and 1 over b minus a. Why would I do this? So notice this is really telling me two things. One, this is telling me that n is greater than 1 over a, but that really just means that a is bigger than 1 over n. So that means whatever my 1 over n term is, it's going to be less than a. So I'm starting to the left-hand side of a. And notice that's essential because you don't want to start with n bigger than a. That would be problematic. So we'll start with some number less than a. And then the second thing that I notice is that n is greater than 1 over b minus a. So that means b minus a is greater than 1 over n. And that just means that 1 over n, as I was saying earlier, 1 over n fits in that gap in between b minus a. So it's smaller than that distance between b minus a. Now, from here, the proof is actually going to look a lot like what we did last time. where what we did last time with the Archimedean principle, where we set E equal to this set, and the set is going to be the set of k in the natural numbers such that k divided by n is less than or equal to a. And then we go through the exact same two processes. So 1, we recognize that this is non-empty. It's non-empty because 1 over n is less than a, so 1 is obviously in the set. And then 2, we notice that it's bounded above. Because we can't do these numbers forever. That would fail. Okay, so since it's non-empty and bounded above, that means that we have a soup exists, and so that means I can look through my problem, and I have a point on here that's my soup, and so that soup is going to be whatever this point is right before A is my soup, and now I'm going to do the exact same trick I did a second ago, and I'm going to add 1 to it. Add 1. So that S, it's actually not S, it is S divided by N, because the soup is the K value. So S over N, and then I'm going to add 1, and when I add 1, I'm going to get in here S plus 1 divided by N for my new term. And now all that's left is to work out the details. So there's a little bit of algebra. I have to prove that S plus 1 over N is greater than A, but that has to be true because S is the soup, so it has to be greater than A. And then I have to be a little bit careful with my algebra to prove that it's also less than B. Okay, I feel like a lot was going into these problems, but I'm confident in you. I've seen you these last 3 days. You've proven to me that you're capable of working on hard things and thinking about hard things, and it's okay to not have all the answers, but we're going to keep working and keep pushing every day. So I want you to do 2 more tasks before you come to class. Task 1.30 and 1.31. This is in the homework section for 1.3. And these 2 problems are basically just asking you what does soup and inf mean? Okay. So this is just getting at the question of, do we understand these words? Do we understand what soup means and inf means, and can we make sense of them? Okay, and then the second thing that we're going to do is choose one of these 2 theorems that I just talked about. So either this density theorem or the Archimedean theorem. The proofs are, they're kind of related to each other. So choose one of the theorems and then rewrite the proof in your own words. So kind of go through my description, keep my description at the front of your mind, read through the proof in the textbook. If you really don't like the proof in the textbook, you're free to go find another textbook, Google it. You can probably find somebody on YouTube doing it. I'm sure you can find it like on Wikipedia or something. But go find a proof that you really like and write out that proof in your own words. And it's a good experience, kind of taking something that looks really messy and then trying to rewrite it in a way that you understand. Great. So those are the tasks I'll put before you when you come to class tomorrow. I know it's a little bit more than we've done in the past, but maybe it's a little bit more pointed and directed. I'll see you tomorrow, and when we come, we'll start talking about these tasks, and then, like always, we'll break out and work on some problems and then share some presentations. So good luck working on everything. Please come see me when